Symmetrical components. Now, symmetrical components, when we talk about the symmetrical components, you should always remember if we have an unbalanced system of n related phasors, that means we have phasors which are related to each other and they are n in the number. N related phasors we call them. Then these phasors can be resolved. These phasors can be resolved into n system of balance phasors. N system of balance phasors which are called symmetrical components of original phasors, which are called symmetrical components of original phasors. Okay, so what we have, if we have unbalanced system and the phasors, that means a phasor will be having a magnitude as well as a length. And just as in the electrical continuity we have any phasor, it's a complex phasor. Then if we have those unrelated phasors, that we can resolve into similar number of phasors, but those similar number of phasors will be balance phasors and system of balance phasors. That those the unrelated phasors which were unbalanced in the nature will be resolved into n number of system of the phasors will be now balance phasors. The n phasors, those n phasors are equal in length, so n phasors will be equal in length, and angle between adjacent phasors of the set are equal. So second is those phasors will be having the length equal and angle between the adjacent phasors, the phasors that will be next to one phasor, that will be next to another, adjacent to it, on the side of it, at some angle of 120 if it's a three-phase system. So those phasors will have equal length and angle will be the same. That means they will be 120 electrical apart in case of three-phase system and similarly in other systems. So in this case, there was one scientist who gave the Fortescue theorem. So according to, for a three-phase system he has given, according to the Fortescue theorem, three unbalanced phasors of a three-phase system can be resolved into three balanced system of phasors which are called symmetrical components. Symmetrical components. So Fortescue has given the theorem about the three-phase system. If we have unbalanced three-phase system, so what we can do, they can be resolved into three balanced system of phasors called symmetrical components. What balanced system will be? In each system, there will be each unbalanced phasor will be resolved into three balanced system of phasors. So total we have, if we have three-phase system, total we'll be having a 9 balanced system of phasors. So that's very clear. So I can write it here. If I have a phasor IB, let's say suppose I have a phasor IB, then in this case, since this is balanced in nature at the beginning, but once the fault will occur in a power system, the balanced nature of the phasor will become unbalanced now. So this is a fault current, or this, let us say this is a fault current, but nature of the current is unbalanced. So we generally we design a system, and nature of the system we assume the system we design as a system as a balanced system. So initially the current will be balanced, any phasor will be balanced. Then this is a current represented in the phase B as a phasor. So it will be initially a balance, but once the abnormality will occur, it will become unbalanced, denoted by this IOB, which is nothing but a fault current. I don't know why they are joining. Okay, so the balance of the fault current, the nature of this will be unbalanced. So what we can do after that, what we do, we resolve this unbalanced system of phasors. That means in the all the three currents will become unbalanced. Let's say phase A, phase A, B, C, in all the phasors there is abnormality. So this, in each phase, the unbalanced phasor current or unbalanced phasor can be resolved into set of three phasors, balanced set of phasors. So in this case, let us say that is I1, I2, and I0. So similarly, in other phases, there will be also three balance, there will be also in three phases a balanced set of phasors. So this is the way we will have in each phase. So total of we will have 9 of balanced set of phasors in a three-phase system. That's what the Fortescue has given a theorem for this one. Now let's do one by one, define them. The number one in this case will be positive sequence components. Positive sequence components. Number one will be positive sequence components. Okay, so let's define this now. Positive sequence components. Positive, I'm writing like this in a short form. Positive sequence components consist of three phasors equal in magnitude displaced from each other. So positive sequence of components will naturally, because I have told you each set of balance phasors will have three, each set of, when the unbalanced phasor will be resolved into the balanced phasor, this is unbalanced phasor, so three set of balanced phasors will be there. So positive sequence component is one of them, will consist of three phasors equal in magnitude, and that will be displaced from each other by 120 degree in phase. 120 degree in phase, having the same phase sequence as the original phases. As the original phasor. So it will be having the same. What are the original phasor will be there? The phase sequence will be original phasor, meaning is what here? Original phasor meaning is whichever the unbalanced phasor will be there. What are the phase sequence that will be having? It will be having this positive sequence set will be having the same phase sequence as that of the original phasor. Okay. Next is negative. Negative sequence components. Okay, negative sequence components in this way will be negative sequence components consist of three phasors. They are equal in magnitude, that is the same as positive, equal in magnitude, displaced from each other by 120 degree in phase, and only differences and having phase sequence opposite to that of original phasor. That's all the differences there. Opposite to that of original phasor. Okay, so next is zero sequence. Third is, so only the difference between negative and positive, that will be, it will be having three phasors that will be equal in magnitude, again displaced from each other by an angle of 120 degree electrical, but only difference in positive, it will be having the same phase sequence as that of original phasor, and while in case of negative, it will be having opposite phase sequence as that of the original phasor. So next is zero sequence components. Just a second. It's calling me. Hello? Zero sequence components. Okay, zero sequence components is three phasors equal in magnitude and with zero phase displacement. That's all. These are three phasors. Sorry. Equal in magnitude and with zero phase displacement. Phase displacement from each other. Zero phase displacement from each other. So these are the three types of zero phase sequences. Zero sequence component is what? Phasors are three. They will be all in equal in magnitude. But in this case, there is no phase displacement at all. There is no phase displacement. So these are the three. So how we can write it? Let us say VA, phase A, fault occurs in voltage in a phase A is an unbalanced voltage now because fault has occurred. So this can be written as VA1 plus VA2 plus VA naught. So first is one is positive secant, second is positive secant, negative secant component, third is. So each unbalanced set, Fortescue has what set? Fortescue has said each unbalanced phasor will be resolved into set of a three balanced phasors. What are those three balanced phasors? Positive sequence number one, negative sequence number two, and zero sequence. So similarly in phase B, now this is again unbalanced voltage now in B. So how it can be resolved? VB1, VB2 and VB naught. Okay. Third will be VC. Similarly, VC will be VC1, VC2 and VC naught. So this is the this is a unbalanced phasor. We have resolved them into set of three balanced phasors. So what are those balanced phasors? Positive sequence components, negative sequence components, zero sequence components. So similar theory will be extended to B, phase B and C. So that similarly we can do. Now how we can represent in phasor diagram, how we can represent for the positive sequence. So this is like this, you can represent it. This is your, sorry, can make it here. One phase will be like this. Okay. Two and okay, this is three. So what will be this? This is a VA1. What is this? This is VB1. This is VC1. Now somebody can ask, sir, what is the phase sequence? Phase sequence is ABC. That is in a clockwise direction. As the clock ticks in this case. That means original phasor will be like this. You have an original phasor. It will be original phasor in our country is in a clockwise direction. Somewhere it's an anti-clockwise, but in India, we consider in the clockwise original phasor. So original phasor will have the same phase sequence. What it will have? It will have a phase sequence A, B, C, but in counter clockwise direction. A, B, C in a clockwise direction. So that's what it will be, having the same phase sequence. So it will be what this will be. This is positive sequence components. Okay. So each will be having a phase displacement of that everybody knows in a three-phase system. It's 120 electrical. So original phasor in our country is in a clockwise direction having phase sequence of ABC. So it will be having the same phase sequence. All the three phasors are equal in length. They are displaced from each other by an angle of 120 degrees. So this is for the positive. Now next is for the negative sequence, how we can draw it. So negative sequence, we can draw it like this. Sorry, this is, I can make it better like this. Okay, fine. Negative secants, let me make it. This is okay. Okay, so this is a negative secants now. Now, what will be the phase sequence? Phase sequence will be opposite to that of the original. So now we will have VA2, VB2, and VC2. Now, if we consider the clockwise direction for the original phasor, so it will be opposite to that. It will go counterclockwise. Now, you can see it's going counterclockwise. A, B coming here, and it's in the counterclockwise, opposite that of clock. So exactly all the three phasors will have same magnitude, displaced from each other by an angle of 120 degree, but having the phase sequence opposite to that of the original phasor, who was having a phase sequence of ABC in clockwise direction, but it is having a ACB in clockwise direction. But if we take it counterclockwise, it will be ABC. So opposite phase sequences opposite in this case. So this is what, this is a negative sequence components. So I'll write it here. Negative sequence components. Okay, let's move to the zero sequence. Zero sequence what? Three phases are equal in magnitude, but there is no phase displacement, so they're very easy for us. So next is zero sequence components. So how we can represent them? Like this we can represent. Slightly tilted normally. There's no question in this case, but they should not have any phase displacement. Like this it should be. Zero phase displacement from each other. So we can write this as VA naught, VB naught, VC naught. All are having the same magnitude, but there's no phase displacement with each other. They are having zero phase displacement. They're not connected to each other at all. So this is a zero sequence components. So then lots of books have shown that how we can draw these phases. I'm not drawing that. Graphical addition we can show that. You can see that's very simple. Graphical addition of components we can do VA1, VA2. Let me show a simple one. I will show. You can just extend it to the others. Momin?
Yes, sir.
Is it clear or?
Yes, sir, Arasu.
Okay. Now let's move to the graphical addition. Simple, I will show phase one. You can extend it to all the three phases. There's no problem. So let me have a VA phase. Now if this is, sorry, if this is your VA1, okay, this is positive sequence. This is your negative sequence. Then this is your zero sequence. And if we take the magnitude of this one, that is resultant of this one, you will always get it. This is equal to VA. I'll be writing for you. This is a graphical addition simply. If this is VA1, positive sequence component of phase A, then this is your VA2, negative sequence component of phase A, zero sequence component of phase A, then these all balance three balance phasors, or a set of balance phasors where we have three set of balance phasors will represent a unbalanced voltage VA. That's what is the theory. That's what is the Fortescue theorem. Similarly, let me draw for others also. Okay, for now another thing. Now let us say for phase B, just a second. Okay, Let's say for phase B. Now this is the positive sequence. Okay, fine. Then this is the negative sequence for the phase B. Okay. Then let's say this is the zero sequence. If we take the resultant of this, resultant of this is fine. Resultant of this will be VB. So this is VB. This is your positive sequence in the phase A. This is in the negative sequence in the phase B. Sorry, phase B. This we are talking about zero sequence in the phase B. And if we take the resultant of this, it will be unbalanced voltage VB. Similarly, if we look for the phase C, let's say this is a positive sequence for the phase C, and this is negative sequence for the phase C. Then let's say this is zero sequence for the phase C. Let me extend this. Just a second. Okay, fine. This is, let me extend this zero sequence. This is positive, negative. Okay. Then this is, you can join it. There's no problem. So this is phase C, positive. Phase C, this is negative. Phase C, this is zero. This one is zero sequence, and this is your resultant VC. So you can draw, this is a graphical addition. You can extend it to any way. There can be thousands of ways to draw it. There's no problem, but just one way I've shown how you can add them. Graphical addition of components. Graphical addition of components shown in figure. Obtain what? Three unbalanced phases. Three unbalanced phases. Fine. Okay, that's fine for us. So operator A. Okay. Now next is operator. See, similarly we had operator J. In case of basic electrical, we have seen that operator J, which rotates the phasor by an angle of 90 degrees. So we have an operator J. So let me write a little bit description about this. Operator J means what? The letter A is used to designate the operator that causes a rotation of, in this case it's not 90, it's 120 degree in the counterclockwise direction. Counterclockwise direction, in the counterclockwise direction. Such an operator, so this is nothing but it's also an operator like J. Only difference here is it rotates the phasor by an angle of 120 degree. Which direction? In a counterclockwise direction. So such an operator will be also a complex quantity, is a complex number like J. It's also J, it's a complex number having a real and imaginary part. Number of unit magnitude with an angle of 120 degree and is defined by A, 1 at an angle of so what is this angle A, operator A having a unit magnitude with an angle of 120 degree. So that's a unit magnitude here. You can see unit magnitude at an angle of 120. If you change this quantity from polar into the rectangular, we'll get an minus 0.5 plus j 0.866. How we get it? Cos 120 plus, in the Euler's form, cos 120 plus j sine. We can write this 1 at an angle of 120 in cos 120 plus j sine 120. Similarly, a square will be what? In a polar, that will be 1 at an angle of 120 multiplied by 1 at an angle of 120. So magnitudes will multiply each other. That will be 1. Angles will add. That will be 240. So cos of 240 plus j of sine 240 will be minus 0.5 minus j 0.866. Similarly, if you have to find a cube, so a cube will be again 1 at an angle of 120 multiplied by 1 at an angle of 120 multiplied by 1 at an angle of, because value of a is like this. So magnitudes will multiply each other in polar and angles will add. That will be 360. So that 360 means itself 1 at an angle of 0. So a cube will be equal to 1. 360 is a complete rotation. Again, we can write it a reference value 0 degree. 0 degree and 360 is same because we are coming back to the same place. So that will be 1. So this is second. So now here, let me draw it graphically for you. How we can see, let's say, a current. Now, let's say we have a phasor like this. Any phasor we have. So three-phase phasor will be having. Okay, so we'll be having like this. And all the phasors are 120 electrical apart. They are 120 electrical apart like this, three phasors. So what will be? If this phasor is 1, then if I'm talking about I rotate this phasor in a counterclockwise direction, So this will be AI and this will be A square I. This will be AI and this will be A square I. Or I can take it like this in a counterclockwise direction. This is because phasor counterclock direction, this will be AI. So that phasor will be with a unit length, that is, this length will remain the same here, multiplied by unit length, 1 unit length multiplied by angle at an angle of 120. So I can represent this I after an electrical angle of 120 degree by AI after again, but in counterclockwise direction. Again, I will represent this AI, that will be A square I. I will remain as same. So similarly, here if I'm drawing, sorry, let us say now I'm talking about this is A. So these are the phase. This is the original three phases. This, and this. Okay. I'll denote it by the red. This as a reference, this and this. Let's interpret the value of A now. Now let's suppose this is 1. That means it is a 1 means itself A cube, because A cube angle we have a reference. Angle we have 1 at an angle of 0. So this is the reference. Okay, this is the reference we are considering. Now after the reference what we have? So at an angle of 120 there will be A. At an angle of 120 here we will be A. So this angle is completely 120. At an angle of from A, this at an angle of 120 or at an angle of 240 from the reference will be A square. So what then will be this one? This is exactly in the opposite direction. So we can write it -1 or minus A cube also. There's no problem. Similarly, this is in the exact opposite direction. So we can write it minus A square. This is again in the opposite direction. This is minus A. Fine. So this is the way we have to interpret the phasor A. This is the way we have to do it. So if we take this reference, 1 at an angle of 0, that will be A cube. At an angle of what? At an angle of 120 degree, that is the counterclockwise direction, it will be having an operator A, whose magnitude is 1 at an angle of 120. Then A square at 1 at an angle of 240. Others you can extend them in the reverse direction and put a minus sign, and magnitude will remain the same, but only the direction will change. That much of vector quantities, I think there's not much in this case. Okay, now this was about the phasor. The next is now if we have, suppose, A4. Now somebody will tell you how to represent A4. So A cube into A. Bases are same, powers can be added, we can, but A cube is 1, so this will be A. So you don't have to write A4. A4 will be equal to A in this case. And then one identity is there. One identity is like this: 1 plus A square is equal to 0. So how you can, the value of this is, in polar, the value of this is, sorry, yeah, A is minus point. We have seen the value. It's minus 0.5 plus J 0.866. This is A square is minus point. Just a second, I want to see. I don't exactly remember the values. Yeah, A is minus and A square is plus. A square is, yeah, both are magnitudes are both in case minus, but angles are negative. Minus 0.5. Real parts are negative, same. and this will be minus j 0.866. If you take the left hand side of this one, we have taken this as LHS. We have substituted the value of a and a square, what we already got. So this will be equal to point j, and this gets cancelled. This gets cancelled, and this will be 0.5, 1 minus 1, that will be 0. So very clearly, if we have identity 1 plus a square, that should be treated as, that quantity should be treated as 0. Quantity will be 0. Okay, next topic what we have an expression for unsymmetrical phasors. Sorry. Expression for unsymmetrical phasors. Expression for unsymmetrical phasors to resolve into, sorry, symmetrical components. Okay. So let's begin with this expression. Okay. Now, number of unknown quantities we know can be reduced by expressing each component of VB and VAC as product of some function of operator A. Let us see this. So we can write here to begin this expression. So what we expression objective is expression for unsymmetrical phasor. That means when the fault has occurred, there will be three unsymmetrical phasors. There will be three those we have to resolve into balanced set of three phasors in each case. So how we can do that and what should be the value? Let's see. That will be 9, but we will shrink it to 3 again. How? With the help of the operator A. So I am writing here number of unknown quantities can be reduced to expressing each component of phase B, that's unbalanced voltage, and unbalanced voltage of phase C as product of some function of operator A and a component of VA. Let's see. That means three unbalanced phasors will be there: VA, VB, and VC. Now VA we have to resolve into 3, VB we have to resolve into 3, VC we have to resolve into 3. That means 9. But what we can do, we can relate the phasor unbalanced voltage of phase B and base C with operator A so that we will get everything in terms of the component VA. Let's see how we can do this. Now I have drawn this. I will copy this figure here. This figure is very important for me. Let me copy these figures. I'll copy this. Copy, and I will put it here, and I'll paste it here. Okay. I'll write it later on. First, it's a phasor. Let's again copy second one. Go back. This is positive. This is negative. Let me copy this. Copy. Let me paste this here. Okay, this is negative sequence that you should know. Okay. Now third is zero sequence. Let me copy this. Or I can write it here. Yeah, let me write this here. Okay, let me copy this side by side to this. Okay, don't require this here. So this is positive. This is positive sequence components. This is negative, and this is zero sequence. This everybody knows. Positive, negative, and zero sequence. Now, going to these original phasors, referring to this figure A, B, and C, you can see. Now you can see here, we can write this, we need to write VB1. VB1. VB1 we can write as how? If we go from counterclock, because we are considering operator A in a counterclockwise direction. You have to remember that, what the definition is there. I will again go through its definition for you. For each one, it's a letter A is used to designate the operator A that causes the rotation of 120 in counterclockwise direction. That is very important for us. Now, what I'm doing here, let's say for me, it's a figure A, this is a figure B, and this is a figure C. Okay. Now here, if I want to write, so what I write here, with reference to figure A, following relations hold good. That means following relations. Let's not write this if you do not want to write this. Following relations exist as per the definition of operator A. So following relationship will exist. What will be? You can have a look here. Now, if I from the figure A, if I want to write, because I need everything in terms of A. That means everything in terms of A. I want to narrow down the uh, number of the balance phasors. I want to narrow down. That means I want to limit them. How I can do that? So from this relation VB1, if I can write this VB1, this VA1 from, I will move from the counterclockwise direction. This is operator A up to VC1, operator A square up to VB1. So I can write VB1 as A square VA1. I think there's no confusion because they are 120 electrically apart. So definition of the operator 1 is it has a magnitude 1 at an angle of 120. That's operator A. So this is operator A. VA1 to VC1 is operator A. From VC1 to VB1 is operator A. AA will be A square. So what is the phasor? Phasor is, I can write this VB1 in terms of A square VA1 very clearly. Similarly, if I have to write now VB2, okay, for phase B, I am writing first VB2. Now VB2 is from figure this one. VB2 is from figure this one. So VB2 can be clearly written as from this figure B. So I will write here for people. Some people may have confusion. So this is from figure A. I will write in the bracket clearly from figure A. Okay, similarly, if I am going to write from figure B, what I am going to write from figure B? I am going to write A is fine for me. I want everything in terms of VA. So VB2 I will write. So you can see counterclockwise direction moving to this. So in term VB, sorry, it's not VBC, it's VB2 here. By mistake, I have written this. It's VB2. VA2, VB2, VC2. Okay, that can be written as operator A into VA2. So that can be written as operator A into VA2 from figure B. From figure B, very good. This figure C does not have any phase difference. So all are same. VB naught will be equal to VA naught. There's no problem. Magnitude is same. We have the definition of the zero sequence component. What's that? Definition of zero sequence component is that, sorry, here we have that magnitudes will be same. There will be no phase displacement. You can check it here. Phasors equal in magnitude, zero phase displacement. That means they are equal. We are not bothered about the operator A in this case, in case of zero sequence. So that you can write from figure C. So this is very clear. Now I want to write similarly the VC1. So VC1 I will write as, now you can see from, again I will go by the figure A. VC1. Now from VA1, how much it is? A operator into VA1. So similarly I will write A operator into VA1. This is again from figure A. Now, similarly, let's move to the VC2. VC2 is here. Now, from operator VA2, how much it is? A, and this will be A square. So, it's very clear from here that VB2, sorry. So, VC2 will be A square VA2. Can verify it here. VC2 moving from here, operator A square, what original phasor is, that means reference phasor is VA2. So that will be from figure B. Similarly, if I have to write VC naught, there's this magnitude is same as VB naught, whose magnitude is same as also VA naught. So all are three are same from figure C. This is from the definition of the zero sequence components. Moment, is there any doubt in these relationships? After that, we can proceed further.
No, sir.
These are very important relationships. We need them. Okay, now what we can do, दो चार मिनट है अभी because we have to utilize time. हमने 2-3 classes miss किए हैं. We have to compensate those classes somewhere in the किसी भी टाइम मैं बोलूंगा तो करने हैं वो compensate, otherwise syllabus का problem हो जाएगा. So now let us call this, okay, now let's call this equation number, this whole set of equation as equation set of equation 1. Now how we have written earlier expression, original phasors, I can write, sorry, here I can write down original phasors expressed in terms of their symmetrical components. So that we know that VA will be expressed as VA1 plus VA2 plus VA naught, positive, negative, and 0. Similarly, VB1 plus VB2 plus VB naught, and similarly VC1 plus VC2 plus VC naught. So let's call this set as equation number 2 set. Now substituting the equation 1 in first. Okay, now substitute this. So what it will become, VA will be written as VA1, and all these things will remain same because we want everything in terms of suffix A. So first expression is not going to change. Second, VB will be, what is the VB1 value in terms of, VB1 is A square VA1. VB1 is A square VA1. What is VB2? VB2 is AVA2. AVA2. And VC naught is VA. We can write VB naught. Okay. Sorry. Can write it in terms of A. We have to write everything. Why we are writing this? So we can write it VA naught because all the three are same. Okay. Now C. VC. Now VC1 is what? VC1 you can see here. VC1 is AVA1. That is AVA1. This is VA1 here also. This is VA1. Okay. VC2, we are writing in this equation, VC. VC2 will be A square VA2. A square VA2. And VC naught is VA naught. These are same. So we'll write this in the matrix form in the next class. I think class is over now. So we'll be continuing with this expression, and we'll be continuing with this symmetrical components. This expression, after that there is with numericals, and then something more will be there. Okay. Okay, Moomin, you can send me the log.
Okay, sir.
Moomin, आपने भेजा?
Yes, sir, मैंने भेज दिया.
Okay, you can leave.
Okay, sir.
बाद में मेरा क्लास है.